So my name is Jefferson Amstutz, and I am an applications engineer as a part of the Scalable visualization group here at Intel, and I'd like to talk to you today about OSPRay. OSPRay, it stands for the Open, Scalable, Portable Ray Tracing Library, and it does a lot of really cool things that I think everyone should know about. So just an outline of what we're going to go through. We're going to talk a little bit about what software-defined visualization is and high-fidelity visualization, as you've already been well introduced to by Jim and Bruce. And then we're going to look at OSPRay itself in some closer detail. So why it exists, the things that it can do, some things you would want to look out for if you were going to use OSPRay, and then some really cool things that have already been using OSPRay. So software-defined visualization and high-fidelity visualization are kind of buzzwords that we've been using lately, but they have some really practical definitions and use cases. So software-defined visualization is the idea that rendering, like making visuals for scientists is just a compute problem. So there does exist special purpose hardware to do this, you know, on GPUs, the graphics processing unit, but rendering is really just a compute problem, and it turns out CPUs can do this really well. There's lots of demand for it, so with science, if you can't see what your simulations are doing, it's not all that useful. Yes, you can grab interesting information straight from a scientific simulation, but you want to be able to see it to really understand what it's doing. And so there are also several HPC systems out there that they don't really want to have special purpose hardware to do these workloads for visualization, and we won't want them even in the future. So a good CPU solution is in demand. So there's some interesting opportunities that this affords when you start using a CPU to do a viz workload. You have full access to host memory. You can do interesting in situ visualization. There's some interesting scalability effects that you can take advantage of, and these are all interesting things that we can now do when you have a good CPU solution. On the high fidelity visualization side, when you're using techniques like ray tracing for visualization, there's more information that is easier to communicate to the visual system of users. There's some interesting flexibilities to be had and some performance benefits that we're going to talk about in more detail. So when we talk about scalable, that means many different things. The easiest, most basic definition that very much applies to OSPRay is the idea that it can run on many different scales of hardware. So this could be something as small as a laptop, run really well there, and scale all the way up to big viz cluster nodes that you would see there in the center, all the way up to even in the cloud with really, really large systems. But scalability also has other definitions and other applications. The idea that you could scale image quality, so you could look at an image there on the left and say, you know, that's pretty good, but I want to be able to scale the quality of that image to be able to get more information out of it, as you can see there on the right, lower image. You can scale really well in model size. So if you have lots of data and you have lots of memory and you have lots of hardware, great. Why don't you use it all to make really great images really fast? And you can scale render costs. There are times where I might want to use a technique like progressive refinement to be able to scale a frame rate, because maybe I want to render at 30 frames a second instead of 10 frames a second. These are things that you get when you have good scalability in your visualization solution. So let's just look at this example in more detail. This is a data set, the Florida groundwater core. These streamlines you see are some interesting water flow, I believe, through the ground. Though I'm not a scientist, so I will not claim any expertise on the data, but rather the visualization of it. It's really easy to see, one, that this does show the data, which is good to be able to render it at all. But this provides a much more visually compelling image, not only that it's pretty, but that it communicates better. And so we're not just talking about pretty pictures, we're actually talking about providing better insight for scientists. And so high fidelity visualization is, I would argue, extraordinarily important to general science, especially computing science. And so when you have a viz tool that's very flexible, you can throw all kinds of different data to it. You could throw volumes, you could have non-polygonal geometry, very complex models. You want transparency, different effects to be able to communicate better. These are all great things to have. And in terms of performance, it's not just preferable to be on par with what an existing GPU OpenGL solution, but rather to be even more interactive than what the GPU and OpenGL can give you for viz problems. So there's another project that Jim mentioned. It's Mpi, and this is both part of the backstory of OSPRay and a part of its current success. So Mpi grew up as kind of a proof of concept to say, can these CPU chips, can these architectures that Intel provides, can they render fast enough and well enough to get all these wonderful things that we want in a visualization system? And it turns out they did a really great job, and part of that solution was that now we have a project that takes ray intersections. So Mpi provides a great interface to do ray intersections and bounding volume hierarchy construction really fast, and it abstracted it away and let that team worry about the performance of that problem and let other people build on top of it. And so that's how it integrates with OSPRay. So like if you see the below images, that those are all really complex models with lots and lots of triangles and lots of primitives everywhere, and they render really fast. And so some just rough high-level numbers you should know of are that Mpi on a dual Haswell or a dual Xeon workstation can traverse rays at roughly 100 million rays per second, and it can build the BVH data structure used to accelerate those rays at about 100 million triangles per second. I mean, these are numbers that are absolutely tremendous, and we absolutely want to take advantage of the work in that project. So stepping back a little bit, if you're unfamiliar with current ray tracing, you might think that, well, tracing rays, that there's no way that could be fast enough. But it turns out that even way back in 2010, ray tracing was already being used in ParaView to render images for visualization. You can even see some cool transparent effects through those cylinders just directly adjacent to the yellow sphere there. So this is something that has been around for a while, but the big key was, can you interactively update your scene and be able to continue to see like multiple time steps or change what you want to see in your visualization application? So there, the big problem is being able to build the acceleration structure fast enough in your ray tracing engine. It turns out, in that previous demo you saw, it took hours to build all the data structures used to trace those rays. But nowadays, with Mpi, we can do both traversal and build so fast that it just blasts through anything you throw at it. And so when you have a fast ray tracer, there's this kind of missing middle ground between application and just ray intersection capability, and that's where OSPRay comes in. And so you might ask yourself, what is OSPRay? And it's this low-level C API. So you have a header that you can compile against, and you can link against the OSPRay libraries and do some higher level operations to be able to give you rendering capability beyond simply intersecting individual rays. And so the primary target is visualization style rendering. So we're not talking about games where we want to render a not overly large amount of primitives really fast. And we're not talking about entire global illumination renderers that like large production movie studios would be using. So high fidelity is an option. So if you have certain set of constraints, you can dial things up and down. I have lots of options. And it turns out that OpenGL style renderings is something that a ray tracer can do as well. And so also the focus is on capabilities, not necessarily just making those capabilities look really pretty. So we're talking about integrating volume rendering and large data parallel rendering on clusters, et cetera, as making the feature set rich for visualization in science. And the focus is on rendering. And so the reason we call that out specifically is because we are not trying to compete with visualization applications. We're not trying to reinvent VTK or provide something like ParaView or Visit, but rather we want to provide a solution those tools can use to provide higher fidelity visualization in those application environments. And so then the role of OSPRay is to really be a workhorse for rendering. The idea that we can abstract away behind the OSPRay API all of the difficulty of rendering applications, rendering images for these applications, and let the viz apps worry about the viz part and let us worry about the rendering part. So OSPRay status, it's about 2 years old, and it's been public open source for a little over a year. So its first pre-alpha was released at SC14 just about a year ago. And it's currently at version 0.8.2, which is an alpha level of progress right now. It's intended for, right now, for integration into existing tools. As you can see in the demos along the side, looking at ParaView and Visit and VMD, these are our current targets at the moment. And right now, the most feature-complete part of the library is to do single-node rendering. So this would be on laptops and workstations alone. But turns out that the MPI capabilities of doing distributed rendering are getting there. They're pretty cool. We have some cool demos at Supercomputing that we'd love to show you. Some interesting primary work that was done by TAC with PV OSPRay is really neat. There's also demos that you'll see of that, and we'd love to show you everything it can do. So the OSPRay internals, at a high level, it uses Embry and ISPC. So we use Embry to say we don't want to worry about low-level optimizations for doing ray intersections, and uses ISPC because we don't want to have to worry about intrinsics. Now, there's a small number of people in the world that love intrinsics, and if you're one of them, you're a special person. But for us, normal people, we like to be able to understand a kind of SPIMD programming model, so a single program, multiple data programming model to get good vector utilization out of these chips, because when you have good vectorization, you have good performance. And so ISPC is our way of doing that in a portable way. So OSPRay provides this rendering layer that provides things like frame buffers and different types of geometry and volumes, being able to distribute on different types of hardware where possible and where required. And it's fully portable across multiple instruction sets and will be future compatible with things like ADX512 and beyond. So if you're a programmer, which most of us in this room probably are, have written some code, these are the things that you would want to pay attention to when you want to use OSPRay. So there are these different higher level components that you need in a renderer. You need the ability to specify a camera. You need to be able to have a frame buffer to paint pixels to. You need things like volumes and materials and textures and models and all of these things, they interact with in a similar way. In fact, that most of these are abstract. So if you need to extend OSPRay to do something else that we don't currently implement, you're welcome to do that. You shouldn't be blocked from that. So for instance, if I have something, some kind of geometric primitive that I would want to do an intersection against, we certainly allow you to go and implement your own geometry type or a renderer, etc. These are all things that are fairly straightforward to do. And so the OSPRay API itself, every object has a collection of parameters that are named by a string. And when any abstract type can take any parameters and it will pay attention to the ones that are relevant to it. So let's look at a lower level example of this. Each one of these types of objects has a factory method. So if I want a camera, I want to do an OSP new camera, as you can see here, and we want a perspective camera. Once I get back one of these abstract handles, I can set some data on it. Like I want to say, where is the camera, the position, and what's the direction that it's looking at. Then once I have those things, I get to tell the OSPRay API, here is the final version of this object I'd like before you paint your next frame, and that's called a commit, to make sure all those parameters make it to all of the things that care about those parameters. So once you've initialized OSPRay and you've created these objects like with these OSP new methods, and you've set all of the relevant parameters you want on such methods, you render a frame with an OSP render frame, having a frame buffer and a renderer, and then you'll get back some pixels, and you can throw them at the screen with the GL draw pixels. It's relatively straightforward. So OSPRay's capabilities are numerous, and so we can look at some of these. Shading is, as I mentioned earlier, very important to communicating to scientists and end users visual information so they can understand what their simulations have done. So we can do all kinds of different types of visualization. 3 of them are called out here. If you want just a standard eye-light illumination, direct illumination, you can do shadows, ambient occlusion, combine these together, different ways of communicating visual information. As it turns out, we have a path tracer in there in OSPRay, and it was even surprising to us when we heard that Eastern Graphics used that to make an architecture visualization application so they could look at different plans for different kinds of buildings, and they went in and specified all the materials and such, and got some really cool, compelling images. And so that was unintended, but also not totally surprising, knowing what OSPRay can do. So here's yet another example of visual cues. So this is just an interesting data set from NASA with some streamlines and some surfaces, and without any kind of extra shading computation other than direct light, it's really hard to see where things are relative to each other. But if we apply some ambient occlusion and some color, it just comes to life. It's very easy to see some depth, and these are all things that can be changed on the fly. If you want to change the amount of ambient occlusion, you want to change the type of shading you want, you can do that all on the fly, depending on what your application needs. One great thing about ray tracing is its ability to deal with large models. And so ray tracing allows us to scale better when we have lots and lots of primitives to subdivide for what that ray needs to intersect against. And this is what Embry is doing for us. So when you don't have really a memory limit because you're on certain limited memory spaces like a GPU, you can, if you have a piece of data in memory, you can just render it, which is a fantastic thing. So we have many different scales of geometry here, and you'll see in future images that I call out. Just pay attention to how large they are. So for instance, we have up to 80 million triangles in that left FIU scene. The Boeing you see in the middle is 340 million triangles, and then we have the 290 million triangle Richtmyer-Meshkov isosurface. And I mean, that's correct. Those 340 million triangles, that's a lot, and it's being rendered interactively, easy to move the view, nice and snappy, a good experience. Another interesting capability is instancing, which is a cool trick in photorealistic rendering. So in this particular case, every single leaf that you see on the different pieces of vegetation is modeled, and none of that's being estimated. But with instancing, the memory overhead of all of that geometry can be greatly reduced. So we're actually rendering 1.5 billion triangles. That's correct. And do it interactively on just a local workstation. But the cool thing is it's not just for photorealistic rendering. It's useful if you had a large data set and you wanted to throw some glyphs on it for visualization, that it's really easy to instance one glyph and not have a ton of memory overhead for more geometry. Though if you have the memory, you certainly could, but this is certainly an option where applications need it. It's also easy to then change scenes and manipulate them and dramatically minimize the cost of rebuilding the acceleration structure to do ray intersections to paint pixels in an image, because you can move things around and keep a local BVH and then use instancing techniques to move them around and not need expensive rebuilds. Another great thing that OSPRay does is it allows for non-polygonal geometry. So if you have something to render other than triangles, OSPRay loves to do intersections against anything that you want it to. So we have some built-in primitives that are showcased here. For instance, streamlines in that NASA data set we looked at. We have spheres, we have the particles there, we have cylinders. That image second from the left is both cylinders and spheres. And then a really interesting data set is that one on the far right, where it's both an isosurface, which is an implicit isosurface. So as we're rendering the volume, we can pull out an isosurface from that. And it's an unstructured volume data set. So it's not just structured volumes that we can deal with unstructured data. And the great thing is you can mix and match all these things all together, which is a fantastic thing. So you'll see demos of or a talk about VMD later from John Stone, but here is some cylinders and spheres and triangles all mashed together in one beautiful image. Volume rendering. So this is something that Viz applications really need, because it's hard to render volumes in a raster environment, especially when your volumes are enormous. And so we decided with OSPRay to have volume rendering be a first-class citizen, meaning it's something that is just directly supported, having cool transfer functions and interesting things. So this is the heptane data set, which is a 256 cube volume. Looks really good. That's cool. But we can do a lot larger than that. So large is a relative term because it really depends on what your definition of large is, usually defined by how big your memory is. So if you have a compute node which has, you know, a quarter or half a terabyte of memory, great, fill it up with a volume and we can render it easy. So for instance, this volume is 2K cubed, which is 32 gigabytes of this really cool turbulence data set. And we can render it really well. And here's another case of that where it's really easy. It turns out that when you have lots of memory, so this is a 2K cubed uint data set of the Richtmeier-Meshkov volume, and it's 8 gigabytes per time step, which is cool because if you have, let's say, 256 gigabytes of memory, now you can load multiple time steps and see this evolve over time. So you can either scale with just a really large volume, or you can take a large volume and have multiple time steps all in memory, rendering them interactively, even the time steps interactively. So with scalability, we want more than just scaling to large data sets. That's hopefully pretty clear. Mpi Distributed Rendering is a first-class citizen of OSPRay. So here in this image, this is TAC's display wall with 80 displays, which is 320 megapixels worth of pixels to display. And all of those nodes that you see, they look like workstations underneath the screens, are actually running one big instance of OSPRay to paint all of those individual images. And so the data distributed rendering, there's data replicated where we can use multiple nodes to all render the same scene faster. For instance, this would take great advantage of that capability. Then there's data distributed where, you know, each, like for instance, if you have a really large volume, you might want to put subsets of each part of that volume on each node so you have more memory to work with. That capability is still under development, but we've had some really cool success with it thus far. So you might be interested in what performance you get in OSPRay. That's everybody's interest, I hope. And so there's some repeatable tests here on this slide where you might say, hey, look, you know, as you know, you scale up, look, you're beating a GPU by a lot. And really the point is not these absolute values of, you know, 14x versus 13x faster than what a GPU can render, because these are all just triangle meshes. We're not talking about all the different types of primitives you can intersect, but really the point to drive home here is look at the scalability as you scale up larger and larger numbers of triangles, that there's a much slower drop off in performance, which is a great thing because in scientific visualization, data sizes are incredibly large. And there's lots of work out there for how to downsample data sets into things that can still communicate visually, but we would argue, why not just render what you have? There's no reason to spend all that time downsampling your geometry. So some early results. It'd be cool if we had all this stuff, but it's only useful if end users can eventually see what OSPRay can do for them. And so early on, and we still have them and we still distribute them, there are some sample applications, what we call a proof of concept, that as an application engineer, I always find it very useful when someone gives me the minimally complete solution to demonstrate the use of an API. And so that's what we've done. We have a volume viewer, we have a particle viewer, just a plain triangle mesh viewer. And these things showcase the API, but they're not tools. So then really our focus in the last few months and the last year or so has actually been integrating these into the various visualization applications, so Visit and ParaView and VMD and others. And so here's some examples we can look at. For example, these are our sample viewers. So we have here on the left just looking at these models, and the images that you've seen before are coming from those sample viewers, but the rendering is all being done by the same library. So the one capability that is very useful is looking at oil and gas workloads. And so these volumetric data sets can be kind of tricky to render, but OSPRay does a good job at them. And if you notice, this isn't just volume rendering. Those colored kind of more opaque things are actually triangle meshes, so we can integrate both volume rendering and triangle mesh rendering together. And that's really useful. We have these slices where you can have clipping planes, and all of these things are built into OSPRay, regardless of our viewer being able to handle those. So if you have a Viz app that wants to have clipping planes, that's a feature that we have for you. And this just showcases some of those things. So some academia examples are some really large models, and Aaron Knoll has a great couple of demos on the machine that's second from the back there with really, really large models. He mentioned earlier that's upwards of 30 billion spheres that OSPRay can just render. And so this is calling out several million particles, but we've already crossed the billion particle threshold, which is really cool. And this is another billion plus model particle, the detonation model. It's just so much data. It's really, really incredible to be able to look at images of these interactively and just explore them. This was an interesting data set, the cosmic web, an early universe model, 12 billion particles. This was being done on a really cool workstation, had 3 terabytes of memory. It's here. And it's here. It's back. It's the one rendering back there. It's really, really cool hardware, let alone the demo itself. As mentioned before, turns out that the path tracing capabilities can be leveraged to do kind of photorealistic things, and that's useful for visualization of architecture, of things that you would want to maybe engineer and see how it's going to physically look, and not just something that you simulate, but something that you want to represent in the physical world. Planning out architecture is a great application of that. ParaView is one of the major visualization applications, and we have a demo of that here in the first workstation on the side. There's all kinds of cool things that you can do in ParaView with OSPRay, and that comes from kitware. And there's currently the PV OSPRay plugin, because there's a plugin architecture that's built into ParaView, and it was initially built as a plugin. So you would create a view that is owned by OSPRay, and there is cool work in the future working on getting that into the core of ParaView, so then everyone can take advantage of OSPRay rendering in conjunction with other types of rendering all in one. And I also wanted to show some other images of VMD, some really cool renderings. These are interactive images. It's really hard to communicate that without a live demo. But an image is an image. You have no idea how long it took that to render. But these, I promise, are exploratory environments that go at great frame rates. And then Visit. Visit is another tool used for visualization by so many people, and we have a demo of that over there by Alok, the third one from the front. And it's also got tremendous progress on integration with OSPRay. So to sum up, we have some what I think are really cool tools that are all about software-defined visualization. And with that, OSPRay fills a really great role of being a workhorse renderer for any kind of visualization application. And we have some early results, but I think they're really compelling, and OSPRay is already doing some really useful things. And because of that, you should go try it out. You can see information about all of our projects on sdviz.org. And you can look at OSPRay specifically up on GitHub. We have information up there, plus the code. Check it out, build it, run it. It's good fun to use. And then you can even dig deeper with PV OSPRay. is pretty straightforward to build, to include with peer review. So I'd encourage everyone to go check it out. And with that, I guess I could take some questions. Thanks for your attention.